And make sure that I sent y'all all an email. I imagine Miss Jones did it too. Make sure that you register for next semester at Navarro. You don't have to pay right away. I don't think there's like a payment deadline that's later. But she wants to make sure that everybody's registered and get all that done because it's been a pretty busy semester, and I'm sure she's like, I don't have time to deal with all this later. So just make sure that you answer that email and get on and register for whatever you need next semester because it only goes till this class technically ends in December and we start a brand new class in January. So yeah, you want to be registered for that. Let's see. Let me turn this on. Go back to the PowerPoints. Wow. We should finish this PowerPoint today. And ideally, I'll have to see how I can get it into Canvas. But ideally today, during 7th period, I get your chapter 3 homework up, and I somehow figure out how to get the lab set up. So yeah, we'll have another lab this week. Wonderful. If you didn't get a chance to finish the rock labs last week, they are open until Friday. So you might want to jump on that because we're getting more and more work that we have to do. Okay, yeah, we're going to talk about groundwater. Let's see what we got. Groundwater, yeah. Zone of saturation, porosity, aquifers, aquitards. Groundwater movement. This is going to go pretty quick. Artesian wells. Oh yeah, subsidence. That's a good picture. And then karst topography. Wonderful. I don't think I have my karst picture. Okay. Here we go. Oh, that's some dark tea. I made tea before I went and did my morning duty in the cafeteria. All the time when I say morning duty, it makes it sound like I'm going to the restroom, and I'm like, I got to add on that I'm doing it in the cafeteria, which again makes it sound even weirder. But I don't know. Sometimes my mind is still a little childish and immature. And yes, we are recording. So yeah, everybody at home, make sure that you go ahead and register for next semester's classes at Navarro. We're going to finish up with groundwater today. We only have 20 slides to go through, and I think we'll go through them pretty quickly. When we say groundwater, we mean groundwater that is, or water that is infiltrated into the ground and is now underneath the surface. So whether it's in a cave, an underground aquifer, or just soaked into the soil, that's the type of groundwater that we're talking about. Groundwater is the largest reservoir of fresh water readily available to humans. So there is more groundwater underground than there is in lakes and rivers and streams. We do have to do a little bit of work to get to it, though, so it's not always easily available to us. Although if you went down a grocery store aisle, you might think otherwise because everything is like spring water. Spring water. I'm sure it's just filled in somebody's bathtub somewhere. So it's a source of 40% of our water that we get. In Texas, that might be a little bit lower. Texas has a lot of man-made lakes that supply a lot of our drinking water. But in general, I don't know if this is over the country or over the entire world, but it's a source of 40% of our water. Drinking water for over 50% of the population, 40% of irrigation water, and 25% of water used in industry. And a little side note, I was at my parents' house out near Maypearl this weekend. It was my mom's birthday. And they were like putting in a new water line right by their house. So they had to dig up this huge like trench to put in a new water line. And we were out in the little horse pen looking at it. And they have an old well there. And it's never worked. The whole time my parents have owned this since like maybe around 2000, 2001. It's never ever worked. And my mom was like, it doesn't work. And I told her, I was like, no, it's just the motor that doesn't work. If you got a new motor for it and put a belt on it, the pump still works. And I went over to it's got a little well house. It's just like cheap corrugated metal. But I went in there and started to pull on the wheel, and the wheel will turn, and then after like a couple turns you can feel it start to get heavy, like it's got resistance to it, and the more you pull the heavier it gets, and then when you let it go it goes back down. And I was explaining to her what that is it's the pump is working and it's sealed. It's pulling water up the pipe from the water table, and the more water you pull up the pipe the heavier it is, and so you have to have something like mechanical to keep on pulling on it, where it's just going to go back down and turn the wheel the other way. So I was telling her, it works if you ever got something to somebody to restore the motor or just bought a new motor for it. But yeah, we get a lot of our irrigation water from underground through wells and stuff, and we'll talk about that in a second. This is important because a lot of times you don't get to see it. Like when you overuse water in a lake, you see the lake level drop really quickly. Has anybody ever been to a lake that's super low and you see like all the trees sticking up from underneath the old trees sticking up? And maybe if like you rent a boat or you have a boat, whoever's driving is telling you, we got to be careful because you could hit something that normally you wouldn't hit because the water levels were low. So the same thing happens for groundwater. We just got to be careful about it because you can't see it. You can't see how low it's getting. So overuse can cause stream flow depletion, land subsidence, which we'll talk about. This is a huge, huge deal. And increased pumping costs because you have to drill new wells, and you have to do things to make sure that you're getting more water out. It is an important geological agent. It forms sinkholes and caves, which we don't have a lot of sinkholes and caves around here. You can look up news stories of like people's houses being swallowed by sinkholes in Florida. I think famously a couple years ago, a guy died like in his bed, just like literally in his house. A sinkhole opened up underneath his bed, and while he was sleeping, the earth literally just took him. And they like searched for his body and couldn't find it. He's just gone into the ground, which sounds like a nightmare, but no offense, there's probably lots of nightmares that happen in Florida. It's not a good place. And then if you have an outlet for your underground water, it can stabilize stream flow. So this is a nice little chart that shows you the total global water, all the water in the globe. 96.5% of it's in the oceans and it's salty. You've got about 1% that is saline lakes and groundwater, salty groundwater and salty lakes. And then about 2.5% is fresh water. Of all of that fresh water, all of that 2.5%, almost 70% is in glaciers and ice sheets. It's frozen and we can't get to it. About 30% of that is groundwater. And then about 1% of that is actually on the surface at lakes and streams and rivers. So of the fresh water that we can get to and we can drink, 30% of it is underground. Only 1% of it is above ground and easy to get to. So groundwater comes from when your rainfall infiltrates the ground. It soaks into the ground. It finds little cracks and little, penetration points where it can get down below the surface. We have a couple terms that we're going to use to describe this. So the first one is zone of saturation. The zone of saturation is where all the pore space, all the empty space in between the little pieces of rocks is filled up with groundwater. The top of the zone of saturation is called the water table. Y'all probably heard the term water table before. I think I heard it well before high school. And the water table is how far down you need to drill to get to some water. If you don't drill down to the water table, your well's going to be dry. There's not going to be any water that comes out. If you drill down into the water table, you will get some sort of water out of your well, or if your hot spring is below the water table, it will have water that comes out of it. The area above the water table is called the unsaturated zone. So zone of saturation, water table, unsaturated zone. Let's see. Porosity. We didn't really talk about this too much in do I have a marker over there? No, took it. we didn't talk about this too much in sedimentary rocks, but this is actually a big part of economically viable sedimentary rocks. Well, this is not too bad. I have this terrible picture. It's not terrible. It's pretty good. Bill, give yourself confidence about your drawings. You'll be fine. Here's my little drawing of the sediments that were deposited by a river. And when these get compressed and become a rock, there's always, maybe not as much as the beginning, there's always going to be some little area in between these sediment pieces, whether they're sand or mud or dirt or whatever size they happen to be. Gravel would be even better because you'd have more space. But there's always going to be space in between these little pieces. In the same way, you see the rack of balls at Walmart, like the bouncy balls that the kids want to stick their hands in and grab out. There's always a lot of space in between those balls because they're round, and round things don't fit together snugly with no space in between them. And then the same thing happens underground. Even if your rock is cemented together and it's a nice sandstone, there's some sort of holes in there in between each of these pieces that is either empty and just has air in it, or if it's underground and it's below the water table, it's filled up with water. And that term that we use to describe that is porosity. High porosity has a lot of available space to hold water, or even better, oil and gas if you're into making money. And so porosity is a really big deal. I think it's also on this page. No, it's not. Do they talk about permeability? Yes. Okay. So porosity is the spaces between the particles, joints, faults. Dissolution cavity. So if water dissolves away part of your rock, that's a dissolution cavity. And then vesicles, if we're talking about igneous rocks, which I don't know that really helps out. Although you can have vesicles like in limestone, stuff like that. In fact, we saw that in the lab where the shells had dissolved away and we had the little holes. Those would be called vesicles. Depends on the size and the shape and the packing and the sorting of grains. Roughly, you can have 10 to 50% porosity in sediments. I would tell you 50% is really high. If you have a rock that has 50% porosity and there's either water or oil in it, you probably have something that's very valuable there. 10, 20% is pretty good. You can make some money off of that. 50% sounds pretty high to me. And the quantity of groundwater depends on the porosity, how much you have. Now, there's another factor in this. Porosity isn't everything. You also need permeability because, let me come back over here to my drawing. Let's say this is like a large scale rock. If I drill a hole right here, like a well, I don't know how to draw a drill, but if I ever drill a hole down here, and this is my well, permeability is the ability for your porosity spaces to be connected. If they're not connected, this well is never going to suck this water out. It's only going to suck out the water that's literally right around the well opening. If you have good permeability, all this water, let me use my red marker. They can see that. All this water that's in between these spaces will flow and connect in between all these spaces, and it will end up coming right over here and get sucked up into the well. And so you need both porosity and permeability. It's probably not likely that you have a high porosity without having good permeability. But in a rock that maybe only has 10, 20% porosity, there's a good chance that almost none of those spaces are connected. They're just kind of isolated, and you can drill a well down there and really not get very much out. That's one of the reasons in oil and gas, especially around here where we don't have great oil and gas, they drill down into these shale layers, which we all saw shale. It was the black rock that was made of mud. It has a lot of little bitty spaces, but not anything that really connects. And so does anybody know the term for what they do to connect those spaces? It's very controversial, and some people want it to be stopped. Fracking. Yes. Fracking, what is fracking short for? Fracture. Yes, fracturing. And so literally they have a rock that has a bunch of spaces. They're really tiny, but a bunch of little spaces that are filled with oil and gas, mostly gas, not really oil for fracking, but a bunch of little spaces that are filled with gas. But the problem is they're not connected. And so you drill a well down there and you just try to suck the gas out, you're not going to get anything at all. So what they do is they drill a well down here, and believe it or not, they literally shove a small piece of dynamite down. Well, actually, no. They used to use dynamite. They don't anymore. They use high pressured water, and I think they do use charges. Sorry, I'm getting a little bit off sidetracked. But yes, they do use dynamite. I mean, it's not dynamite like a stick of TNT, but it's an explosive charge. They put it down the hole, and actually sometimes they have like little holes drilled in the side to kind of make sure that it's directionally placed. But they detonate that in the hole, which causes a bunch of cracks to come out everywhere. And these cracks connect all these pore spaces. It goes all different directions, usually just in the layer they want it to. And then the controversial part about the fracking is they pump, usually it's pretty bad stuff. They pump like diesel fluid and salt and all sorts of other materials in there to spread all those cracks open and to pressurize it. And what will air do in water? It'll float to the top. And so that's what they want. They want to flood all these little cracks with water, which is going to push the air back to the drill well, and it'll come back up the pipe, and they can extract the gas from it. The problem is it's not like clean water that they're doing, and when you use dynamite, you can't really control where your cracks go. So if it goes into an upper layer, it could contaminate a water table and kind of make our water undrinkable, which has happened in certain places. So yeah, their fracking is very controversial, and to be honest, the oil industry has done nothing to make it any better. They're basically like, we make billions of dollars, and you can't stop us. So, haha. And I used to work in the oil industry, so I've seen and smelled the terrible fracking fluids that they use, and a lot of stuff around here. They literally use diesel. They take diesel gas and pump it down into the wells. So it's not like it's like just water. It's almost never just water. So yeah, fracking is very very controversial. But what they're doing there is trying to create permeability that didn't exist before. They're trying to connect those porosity spaces so they can actually get the gas out. Then we have two new terms. Aquifers is not new to you. Aquifers is what holds the water. Aquatards is an impenetrable layer that prevents water from escaping. So it's kind of like the opposite of aquifers. An aquifer has porosity, it has permeability, the water soaks into it and it can flow around. This is where we get a lot of our drinking water from. An aquitard kind of holds that water in. So from the scientific term retard, you're preventing something from happening. Like fire retardant is preventing something from catching on fire. Aqua retardant is preventing water from going through. Although I always think of it as like a leotard bathing suit, like an aquatard, which makes me laugh. I don't know. I think it's funny. Okay, so here's a picture of aquifers and aquatards. Here's your main water table. So this is all saturated with water. This is your zone of saturation. You can see above here, there's a little bit of water in between the pore spaces, but mostly air. Down below the water table, all of the pore spaces are filled up with water. And in this picture, you can see that the pore spaces are nicely connected, and so you could draw this water out. Where the land dips below the water table, you will have a spring. So this is like a freshwater spring. So this is a creek that really won't stop running until the water table gets completely decimated. We don't have a lot of these around here. Has anybody ever been to like a natural hot springs? They're super nice. If you're ever driving like on vacation and you see a little sign that's like hot springs, As long as you don't have to pay money at like a resort, which usually you do. Stop and take like a dip in the hot springs or just dip your feet in. It's usually really crazily hot. I stopped at one in I think the town's called Las Vegas, New Mexico. It's not the Las Vegas. Very, very different place. But they have like a natural hot spring and they have like 4 or 5 different pools. The main pool is the hottest because it's come right out into the main pool. But it's almost too hot to enjoy. So they let it spill over into another pool that they built, which is a little bit cooler. And that spills over into another pool, which is a little bit cooler. So you have like all these options of your heat level that you want instead of just having one. So in this picture, what they have also, this layer right here is an aquitard. So this is like a thick layer of clay that somehow got here while all the sediments were being deposited. And it doesn't allow water to flow through it. So when it rains and all this water infiltrates the ground, this layer kind of holds up an elevated water table. It keeps it up above the normal aquifer that's down here. And so you can see you have a zone of saturation up above it. You can see where this layer meets the hillside all along here. You have natural springs that come out and feed this little hillside. And then they've illustrated two things. They have a well that was drilled up here, which first off, if you're drilling a well at the top of a hill, you probably don't understand. You didn't pay attention in geology class. Because A, even if there is water around here, you're going to have to drill really far down to get to it. B, water always goes downhill and goes to the lowest elevation that it can. So starting at the top of the hill to drill a well is not necessarily the best plan. They went down a little bit, which I don't know that they knew this, but they went down a little bit, drilled a well that's probably like half the depth and cost half the money of the original well, and actually hit this elevated water table so they can get water out of that well where they can't out of the first one. Okay, it's important to know that groundwater moves very slowly from one place to another, even within a rock that has a lot of porosity. It takes a long time. So the typical rate is only a few centimeters per day. So in most wells, you're not going to be able to pump like thousands and thousands of gallons every day. You can pump every once in a while, and then you kind of got to let it reset. And what happens there is if you pump too much, you actually get something called, hold on, I'll come back to all this because they should have, maybe I should move this slide around. Where's the cone of depression? What? Did I miss it? I must have missed it. Surely I missed it. Oh, drawdown. I saw it. Did I see it? Oh my gosh, this is embarrassing. Confined water table. Drawdown. Cone of depression. There it is. How far back did I go? So they would have the hot springs and the geysers in between. Okay. If you pull too much water, it takes a long time for the water to move to where your well is. And so what happens is a phenomenon called drawdown. And this is a human thing where we overindulge and we pull too much water out of an aquifer. And every once in a while, if it's a really dry period, we haven't had one in a couple of years now, you will hear about aquifer problems here in Texas, where we're pulling too much drinking water out of the aquifers, and we need to try to conserve. And what they're worried about is this. If you have a well that is pulling too much water out, it takes a certain amount of time for the water that's in the aquifer to actually get back over to that well. There's not really an example in a cup with a straw because the water gets to your straw pretty quickly. But you can see here, they pulled out a bunch of water for their farming. Now the field's all nice and green. But they have this cone of depression here. And basically the water table gets depressed all the way down to the well itself. And it takes a very long time for the water to actually get over there to feed into the well. So this is a very bad thing. And on top of that, if I go back, one thing that we're going to talk about in a second, if you remove all the water from these pore spaces, you can actually have collapse of the land. It can get squished down because the water in many ways is holding this up. we learned in chemistry, because I know, because I taught all of you, that water is not compressible. It actually holds its volume very, very well. And so even with a whole bunch of weight of land on top of it, this water isn't really getting squeezed. And if you take all the water out, the land can then sink down. And we will talk about that in just a couple slides. So we talked about that. Springs, I mentioned springs. Basically, if your land, your surface level of your land goes below the water table, a spring will happen where you have water just flowing out of the surface. I talked about the perched water table. That's what we saw in the image back here. That's your perched water table above the other one because of an aquitard. Here's a picture of some nice springs coming out of the hill, just like we saw in the other picture. Hot springs have a nice temperature to them. The temperature increases about 2 degrees centimeters every 100 meters below the ground. So you're getting that natural heat coming off of the Earth's interior. And then they say generally water is at least 6 degrees warmer than the average annual air temperature. So if it's like 90 degrees, you could have like 9600 degree water. And geysers, was it you or somebody else that went to see the geysers? It was one of my chemistry students, I think. Or no, maybe it was somebody that comes in during activity period. Somebody went to, hold on. It's on the tip of my, it was Weston. Weston went to Yellowstone. Yes, with the geysers. I don't know why I'm having trouble with words right now, but Old Faithful. I almost said Old Glory. Old Faithful, the geyser, and he had some nice videos of the geysers. And basically, your water heats up until it has enough pressure in it that it shoots out of a weakness in the rock above it. And so you have to have a chamber under there. It's got to get filled up and kind of heated up, and then it shoots out. And so there's a lot of geysers in Yellowstone. Or is it Yosemite? It's Yellowstone, yeah. Yosemite is like California. Yeah. All right. We already talked about drawdown and the cone of depression. An artesian system is where you have a well that kind of shoots up water. Here is an example of an artesian system. So the water table is actually way up here. You have it confined in between these two layers. And so when they drill a well down here, they don't even have to pump the well because the top of it is below the water table. And so it's constantly just flowing outward forever. And so they've made a nice fountain out of it. And as long as this water table is here and filled up, this well will just shoot water out 24 hours a day. And so they got some close-ups of what's going on there with the artesian wells. Confined water table, aquitards, we've already talked about those. So what are some features that result when groundwater reaches the surface? Springs, perched water tables, and hot springs are all features of when it reaches the surface. How else does water reach the surface? We talked about geysers, wells, and artesian systems. Wells are, of course, the man-made ones, and artesian systems are too. Here's an important thing. This is subsidence. This is problems when we as humans overpump groundwater and take too much out. And this picture is actually really crazy. This is a real place. It's a real thing that happened in the San Joaquin Valley in California. They had a water table there, and they pumped it for farming purposes to irrigate their crops and water their land. Way up here is where the level of the land was, like where this guy would have been standing in 1925. And then they kept pumping the water, and all the water that was essentially holding up the land and filling in those pore spaces was removed because they overpumped, and all those pore spaces collapsed, all the sediment got compressed, and the land level kept falling and going down and down and down and down. This isn't even recent. This is 1977. And so this guy's standing here in 1977. This is 30 feet lower than it should be. When it does rain, I would probably put money on it that this area floods now because it's 30 feet lower than it naturally should be. And so they probably have flooding problems along with that. So subsidence is a big deal. You want to make sure that you're pumping water responsibly. You're not over pumping, and you're working with a geoscientist to make sure that your movement time underground in your aquifer is sufficient enough to replenish your well, and you're not having any land subsidence. And if you are, you need to start buying water from somewhere else and not ruin your land like this. Probably a lot of problems came from that. So, what are some environmental problems associated with groundwater? Groundwater is not a renewable resource, especially on a short timeline. You only have a limited amount of it, and things can change. And sometimes your infiltration stops, and your aquifer won't really replenish itself. Ground subsidence, like we saw in that picture, and then obviously water contamination, which is kind of something that's happening in Houston right now. Hello? Yes. Okay. But are you taking the ASVAB too? Oh. She said when the bell rings, go to the library. ASVAB it up. What do they test y'all on? Is it just general high school stuff? Did you study?
No. I've taken it before.
Oh,
It's like aptitude, kind of.
Yeah, I know. So it seems like it probably wouldn't be a lot of like
it's like
SAT questions. Yeah.
There's one section on I got it really bad on that one. And then there's like, it's kind of just like math.
Mechanical math, general science.
Yeah.
Are you thinking about joining the military?
Oh no, I took it last year because I Miss Jones was like, well, because I didn't really know what I wanted to do, and she was like, well, it's like an aptitude.
Yeah. We do that here, and it's a good thing because we actually get to take a lot of these tests here at Palmer, where smaller schools you'd have to drive somewhere else to take them. But the only way we can actually do that is if a lot of people take them, and so they kind of I don't want to say coerce, but they kind of go around and are like, hey, you should take the ASVAB, you should take the SAT, you should take the whatever. There's something else coming up that they're going to be taking. But yeah, because if you only have like 5 people do it, we're not going to be able to continue to do it. So I think on average here in this school, way more students take the SAT than have like the college acceptance letters in the hallway. It's just a numbers game. But again, like being registered to vote, go ahead and do it. That way you have a score. And if you do want to go to college or take some classes, you don't have to do like I did and like 6 years after you graduate high school, go back to Waxahachie High School and take the SAT with a bunch of high school kids, like as a fully grown adult. That was weird, but I had to do it because I never took the SAT in high school. Okay, they talk about caverns for a little bit and caves. My advice is if you're ever on vacation and you get to go inside a cave, go inside a cave, especially if they turn the lights out, because you've never seen darkness until you've been in a cave with the lights out, because they're like, turn all your cell phones off, don't try to take any pictures, cover your watches if you have like a watch that has lights on it, and we're going to turn the lights out for just a couple minutes. And you're like, yeah, it'll kind of be dark. In your house with the lights out and it's like midnight, it's not really that dark. You just sit there for a couple minutes and you can see stuff. In the cave, you're like a half a mile underground or something. There's no light at all. Like it is as dark as you've ever seen it. It's really crazy. So if you ever get a chance to visit a cave, I would highly encourage it. I think I've been in a cave in Texas. I think I've been in a cave in Arkansas. And I would like to go in Arizona. I know Arizona and New Mexico have a couple cool caves. But basically, caves are when your water dissolves away rock. Usually it's limestone. Limestone is easily dissolved by water. And so your underground aquifer hits a layer of limestone, so starts to dissolve it away pretty quickly, and your caves and your caverns form. Karst is a new term, not a new term, but a new term for y'all. That's basically like sinkholes in the ground. Let's see, they talk about karst topography. So see all these like indents? This is a big thing in Florida. It's basically little circular holes that get dissolved away, like caves, but at the surface, everything collapses down into them. This was one of the first posters that I published, like a scientific poster that I got published as a college student. My teacher came to me and was like, I want you to do some work on karst topography. And basically, the idea was just for y'all, you have these holes. I'm running out of room to draw stuff. You have these holes in the ground, essentially. And when you're doing geophysics, it's all about the speed that your sound waves travel through the rock. And you need to know that speed to be able to understand your depths and how things are moving. But if I have this hole and it's well underground, there's layers above it, but it's filled with a different material, it's going to have different speeds. And so if it's a different type of rock, your sound waves are going to travel differently through there. And so I had to do a lot of work to try to analyze if the drop downs that we were seeing were amplified because of the speed change, or if the material was very similar and it was just a normal drop down. And it was actually really cool. And he made me do a poster out of it. I had to take it to a geologic convention and kind of stand there for a couple hours and talk to any professionals that came by. I'm like, hey, this is a cool poster. What's it about? And I kind of talked to him about it. And it was kind of my first delving into like actually explaining the scientific work that I was doing as a college student. So I have a love affair with karst topography, and it's pretty cool. You can see some nice karst stuff in Florida. We all know about stalactites and stalagmites. Tights are on top because they have the T. Mites are on bottom, and that's basically the mineral-rich water that has dissolved the limestone, dripping down from the top of the cave and forming your stalactites. And where it hits the floor, you get even more deposition, and you have stalagmites. Let's see. Here's some karsted landscapes. What's happened here? The karst holes, I believe, it could be the opposite. The karst holes have been filled in with a much harder material, and then as erosion has happened, the harder material in the karst hole is what's left behind and is actually stuck up. So it's almost like reverse karst topography. It's interesting. And then that's it. We finished. Yay. So today I will try to get your homeworks in for this chapter, maybe even for the next chapter so we can get started on it. And I will also try to develop the lab in Canvas so we can start to talk about the lab tomorrow and do some interesting things there. Thanks for tuning in, people at home, if you happen to watch this video. If you didn't, I will look at my YouTube analytics and I will know that you haven't watched the video. So everybody have a nice day, and I'll see you tomorrow.